All right, good afternoon, everyone. Welcome to week 4. Do please note that I have made some announcements with some good links to take advantage of, as well as some information on the dark web. For this week, again, we're doing network fundamentals. Here's your outcomes. And then we have some reading in chapter 6, lecture presentation, and the quiz. Again, the quiz is really no different than anything you've had so far. I do want to call out again, I've done this a couple times, but the program assessment quiz, please go in, take that. Don't feel any stress about it because you're not going to be held accountable for it. We just, again, want to assess the knowledge level that you have coming into the program, okay? So regardless of whatever score you get, I'll change it to 100 before we go to submit for final grades. The final exam opens up on August 9th, okay? I think there's an announcement out front that says August 8th. I need to change that. It's August 9th at like 1 o'clock in the morning. Yeah, here we go. I'll get that changed. All right. Let's talk quiz from last week. So quiz 3 for malware. Overall class average was 91.47, which is very good. About where I expect, honestly. And there's really only 2 questions that I found concerning, and that was question 45 on the master list, which is here. It says, a security analyst at ABC Incorporated is deconstructing malware that infected their network recently. Some of the characteristics that the analysts recognized were that the malware code changes with each infection, and that the malware seems to present with the same functionality. Excuse me. Below is the depiction of screen captures that the security analyst was able to extrapolate from users' infected systems. Okay, so this is going to be polymorphic because it's basically doing the exact same thing every time. Okay, the wording is just a little bit different. I think I maybe even used this specific example when we talked about it last week. But metamorphic can evolve capabilities essentially. So there's that one, and then question 48. So here we talk about developers have been conducting reverse engineering on malware that has been seen in the wild. The malware seems to inject its malicious code throughout the body of a legitimate program. That right there is the most prolific statement in all of this, okay? The malware only runs when the host application is ran and ends when the application is closed. Oh, excuse me, I need more coffee or something. Okay, so due to the characteristics of the malicious code, how has the malware been developed to hide? And so the answer here is insert, because of that simple statement that I pointed out earlier. It injects its malicious code throughout the body of a legitimate program. And so insertion was one of the methods of hiding malicious code that we talked about last week as well. So aside from that, I didn't have any concerns, any other questions. Zaquan, did you want to bring anything up?
Yeah, about the final exam, we can ask it at the end if you want
Okay.
to.
Okay, yeah, that's fine. And then anybody that's watching this asynchronously at home, if you have questions or concerns about the week 3 quiz, shoot me an email. I'm happy to answer any questions you might have. Now, for extra material this week, I wanted to, because we're doing networking, I wanted to introduce you to a tool called Cisco Packet Tracer. And this is a very popular tool for doing network diagrams. And most of you are going to end up taking CYBV 326. That class is the Wireshark class. I think I've mentioned it here in this class before. And your final exam is to make a network diagram. And there's a million different ways to do that, okay? So don't think that this is the only way. But if you are looking to go above and beyond, Cisco Packet Tracer is going to be your tool for that, okay? Even if you just want to use it as a learning tool. So basically what this thing does is you can throw specific routers, switches, IDS, IPS, like literally any kind of network tooling onto this graph paper, essentially. And when you click on it, you can configure it as if you're actually configuring the router itself. Okay, like you literally have to click on, like push the button to go turn the router on, and then you can log into the command line interface with the correct serial cable, and it's like super in depth, right? And you don't have to be that ultra in depth for your 326 final, but I'm just saying like this would put you over, above and beyond. All right, so the next tool I want to show you is Cyberopolis again, right? So when you go to Cyberopolis, And that's portal. Oh, it logged me out. Portal.cyberopolis.com. Just give me a second to get my code. There's a feature once I get in there called NetSim. And NetSim is something you're going to use for CYBV 479 for your cellular class. That's your wireless technology class. And so you should all have access to this NetSim portal. Now, if you have full functionality for all these different modules, I'm not sure, but at a minimum, you should have networking. Okay. And so you can click networking, kind of mess around with it, and you can do practice for architecture, message flow for how things work. I mean, some of this stuff is really important, right? Like ARP request, web page request. We've got DHCP requests, DORA, right? Discover, offer, request, acknowledge. These are all things I think we're going to talk about DORA in this class, but if not, we'll definitely talk about it in 326. But there's so much. Here's the three-way handshake. I think we talk about that this week or next week. So there's a lot of stuff that you can do inside NetSim as well. All right. Let's go ahead and dive into the lecture for this week. So welcome to week 4. Again, we're talking network fundamentals. Please take a second to look over what I'll be talking about today. All right, we'll go ahead and move on. We're going to start out with an overview of networks, and then we're going to dive into transmission media. And Zaquan, I just got a notification that my network's unstable. Can you hear me okay?
Yes, I can.
Okay, cool. So we're talking transmission media. Okay, so starting out like high level, there's wired and wireless networks. Okay, so wired networks, you can either have twisted pair. Inside of twisted pair, there's unshielded twisted pair, which is what you see here without basically some aluminum cladding. And shielded twisted pair, which we'll see on the next side. Okay, so this is unshielded because it doesn't have an aluminum foil basically wrapped around it. If it does have the aluminum, that's shielded twisted pair. Right, there's coax cable and optical fiber. We're going to talk about the differences of these and why each one serves its purpose. And then under wireless networks, this is all being transmitted via radio frequency. Okay, so there's satellite, microwave, cellular. WiMAX is kind of a deprecated technology at this point, but everybody uses Wi-Fi, wireless fidelity. Bluetooth is very popular as well. And Zigbee and Z-Wave are actually more popular than you probably realize because they power a lot of the home automation things that you use in your house. All right, so diving into twisted pair, okay? As I mentioned before, there's a difference in twisted pair. There's shielded twisted pair and unshielded twisted pair. And the reason for shielded twisted pair is to help reduce something called electromagnetic interference, or EMI. And EMI is basically interference on the line. And so if you can kind of make this analogous, or make the analogy for a radio, right? When you can hear the radio super clear, there's no interference, and all of a sudden it gets staticky, right? The same thing can happen with networks, except with network, it's packet loss, and you start lagging and having issues with, connectivity. But EMI can cause that. And so the shielded twisted pair is slightly better for defending against EMI. But just know that out of all the wired networks that we're talking about today, twisted pair is going to be the worst when it comes to, susceptibility to interference of EMI. Now, down here, there's a bunch of unshielded twisted pair categories. You don't need to memorize this, okay? But there's some things that I do want to point out. Inside your house, you're probably running no less than Cat 5. You're probably running Cat 5e. And in some places, you might even be running Cat 6 if you ran it like probably yourself, okay? The difference here on the different categories, at super high level, they start introducing more twists per inch is one part of the rating. It also is more durable for being able to increase bandwidth and electricity to being pushed down the wire. Okay, so that's why you see the data rate going up for each one of these categories. Now, max length is somewhat debatable here. Okay, this says 100 meters. Now, I used to be a network technician, sysadmin, so to speak, when I started out in this field. And I've seen cable you can run past 100 meters. And I've seen cable that you couldn't run to 100 meters, okay? It literally just kind of depends on the manufacturer and basically how that specific cable is made, okay, on what you're going to get. But just know, like, industry standard is like, don't run this past 100 meters, right? That's the good breaking point, I would say. All right, coax cable. This is the upgrade from twisted pair. Okay, the big difference here that I want to impart upon you is that you get faster speeds via coax cable. It's a way more durable cable. You probably have this running from your wall to your all-in-one device that your internet service provider has given you, and it's really resistant to EMI, electromagnetic interference. Okay, so pretty decent step up when we talk about from twisted pair to coax cable. Again, I don't need you to memorize the cable types down here. The big takeaway here is that, one, you get better speeds, much more durable cable, and highly resistant to EMI, okay? And you can also run this a lot longer than twisted pair. And then finally, we have optical fiber, okay? And so we're utilizing like light pulses, like electrical pulses on the coax cable and the twisted pair, but optical fiber, we're using light, okay? And so you can find optical fiber made with plastic cladding. So that's what you see here. And then sometimes you see it with glass. Okay. And glass ones are a really big pain. If you step on them, it can literally shatter all the tubes in there. So pretty fragile. But this is going to be completely resistant to EMI. It's going to be incredibly fast. I mean, some cities have, a lot of cities have gigabit internet, but some cities have 2 or more gigabit internet. That they're able to run for that's just for residential. And so if they're running that for residential, you can imagine what they're running for commercial, because commercial gets a lot more. So some other things to kind of point out here is that there's a couple different types of fiber optic cables. There's multi-mode and single mode. So multi-mode is going to be your less expensive. It has a larger core in the center, lower performance. Single mode optical fiber, more expensive, smaller cores, and higher performance. So now we switch gears into wireless networks, right? So there's, again, a lot of different technologies in this space, but at the personal level, and we're going from smallest to largest types of technology here, Bluetooth. Bluetooth is, you have to be like within 30 feet is what most of our devices are going to operate in. Now, there's different classes of Bluetooth, and Bluetooth can actually, in its highest class, in class 1, can go really far. I want to say it's like 200 foot or something. But most of the devices we have on our interpersonal every day is going to be in that class. I think it's 3, where it's up to that 30 foot. There's also Wi-Fi, right? That's pretty localized as well. And then back in the day, we had IRDA, right? Infrared Data Association. So I might be dating myself here a little bit, but back in school, I remember when they came out with the Palm Pilot, you had to stand in front of your partner in order to transmit a text message to him, right? Or a Word document or whatever you were sending him. You had to have line of sight, right? That's infrared. You don't see that a whole lot anymore, but it is certainly a data capability. Zigbee and Z-Wave. Z-Wave is not up there, but just know, again, that's for like pretty close hold area, localized. You're trying to share messages between home automation devices. And then UWB is ultra wideband. Think like 5G networks. And then you have your wireless local area network. So when you think local area network, think like we used to call this SOHO, right? Small office, home office. And so whether that's like 1 floor in a building for like your workspace, a commercial workspace, or if it's your home office, right? That's kind of the small area that we're working with, right? And Wi-Fi, Bluetooth, and Zigbee to absolutely work with that. As we step into the metropolitan area network, this could be multiple buildings in a downtown area that are geographically dispersed, right? They could be within a couple miles of each other. So much more bigger geographic area for metropolitan area network, right? And in fact, microwave communication, in some cases, it has to be line of sight, but you can shoot from city to city. Like you can shoot microwave communication really far, actually. And it tends to be a secondary, maybe even tertiary communication medium for a lot of countries in their like wartime contingencies. WiMAX, we talked about, that's deprecated, like satellite type of internet. The popular satellite kind of internet nowadays is going to be Starlink. And I'm actually teaching on Starlink network right now. And then limited Wi-Fi, just meaning that, so in some instances, you can basically repeat from the base station enough to be able to cover a decent geographic area. And those of you that live in Texas, I want to say it's either Houston or Austin actually provides like public Wi-Fi in the city, right? So you can walk around the city and have access to internet. Then we have wireless wide area networks. And when you think WAN or wide area network, this is a huge geographic area. This is the entire Earth, right? And how the Earth is able to communicate, right? So we have cellular technologies. We talked about how microwave can shoot cross-country, basically, in satellite communications. There's also transatlantic cables that get buried in the water to be able to connect different geographic areas. So let's talk access points and base stations and what's the difference, right? Well, an access point is going to be what your like Wi-Fi access point is going to be, right? So that's going to be in your SOHO. The base station is going to apply to cellular technologies. And again, you're going to dive way more into cellular technologies when you get into CYBV 479. And clients can be a ubiquitous term used for laptops, desktops, mobile phones, right? Any kind of device that you may have can be considered a client, okay? They can be networked together, meaning that the traditional way of networking is, you connect to either your access point or your base station and get your connectivity from there. However, nowadays we can do hotspotting and you connect devices to each other in order to provide internet access, print capability, whatever it is, okay? Now, when we talk about the evolution of security for wireless communications, right? Now we start out with WEP, which is wired equivalency privacy. And WEP was introduced to literally say, hey, we have a comparable security mechanism to wired networks. WEP didn't last long. In fact, without going into the cryptographic modules, the initialization vector, which was a random sequence of numbers to basically introduce additional randomness into the cryptographic algorithm, was reused every 5,000 packets. And so those of you that out there that have played with Wireshark at all, 5,000 packets happens in literally just a couple seconds. And so if you just sat in on the traffic long enough, you'd be able to pick up the key from WEP. In fact, you can crack it in under, I think, literally seconds nowadays. And then you have access to whatever is going on in the network. So a direct replacement was WPA. Okay, Wi-Fi protected access. WPA sought to literally just address the downfalls of WEP without advancing the technology at all. WPA lasted even longer. They tried to, or I'm sorry, then they introduced WPA2, and then with WPA2 there came personal mode and enterprise mode. Okay, the big difference was that with enterprise mode, you had the option to introduce something called 802.1x, which is port security. And so you could basically marry a specific computer to a specific port, wired or wirelessly, as a security mechanism. They have since introduced WPA3, but to be honest with you, I have not seen this ubiquitously implemented quite yet. AES is advanced encryption standard. We're going to get more into that in the cryptographic module in week 6. E0 and A5, all again encryption stuff. AES is going to be the best encryption that you can use today. Okay, some form of that. Usually AES 256. E0 is for Bluetooth and A5 is for cellular technologies. Okay, and each one of these all have their own problems. Okay, you're going to come to find that there's literally not a single technology out there that doesn't come with its own problems. All right, so let's dive into network devices, right? Let's start recognition here. One thing I really want to point out, I talked to you multiple times already during this lecture alone about how in 326, your final exam is a network diagram, okay? What you're seeing up here in this top right area is that is specifically industry recognized symbology for a hub. Okay, and all of the devices are going to have that, right? Like this is an industry standard for a bridge, industry standard for a router. Okay, that's the kind of thing that's actually a requirement on the 326 final exam is that you use the industry approved symbology for these devices. Okay, so if this is the first time you're seeing this, that's great. No action you need to take besides inoculation and say, hey, I recognize that this is a thing. So hubs, we don't really use hubs a whole lot anymore. There's certainly some specific niche use cases for them, but they're kind of a security vulnerability. And the reason that is because it replicates all the network traffic on the ports. So basically, any computer that's plugged into this hub, as traffic is coming in, let's say destined for the computer that's plugged in on this one side of the port, everybody's going to receive the message. Okay. And that's a problem, right? You could think of it as instead of having individual lanes to send your traffic down for like cars, like all of it kind of dumps into one area. And you can imagine the congestion that occurs, and congestion does occur, right? So people can listen in on your traffic. That's also considered a large collision domain. So when you go to send traffic out of the hub, if another computer has sent traffic at the exact same time, those messages or those packets of data, electronic pulses, whatever you want to call it, are going to collide. And that's also going to be a problem. And so without getting super deep into it, what ends up happening is the computer's notified its traffic wasn't sent. There's a random back off algorithm that occurs to say, hey, I'm going to send it at 10 seconds. The next computer says, hey, my random algorithm says I'll send it 15 seconds. And then they're able to kind of deconflict that way. The more computers you have, the more that becomes completely unscalable. Okay. And so that's why we call it a large collision domain. It's not good for security. Okay. There's not a lot of configuration you can usually do on a hub. Okay. And we haven't talked about the OSI model yet, or Open Systems Interconnection model. We're going to talk about that next week, along with the TCP/IP model. But just understand this works at layer 1 of the OSI model, which is generally just speaking like RF radiation, electrical pulses on cables. Okay. All right, next we have bridges. Okay, bridges can operate at layer 1 or 2, depending on what's going on, but you can break up those collision domains by utilizing a bridge. There's 4 different types of bridges, and they can be wired or wireless, capable. But simple bridging is going to take 2 networks, connect them together, and decide frame by frame if it needs to send it across the bridge. Okay, so this diagram works really well for kind of showing that, right? Instead of having 4 computers plugged onto hub 1, you're able to break that up, because as we talked about before, the more you try and scale that, it doesn't scale. So we broke up, instead of having 4 computers on one hub, you now have 2 computers on 2 hubs, and you have the bridge just in case that host D needs to talk to host A, or host B needs to talk to host C. Okay, so that is possible. So again, that's simple bridging. Multi-port bridging connects multiple networks. So if there was 3 or more, then it would be able to, decide frame by frame if it was going to send that traffic on. Transparent bridging utilizes a forwarding database, right? So similar to a switch, which we'll talk about in a second, the switch has a CAM table, a router has a routing table. This is just another kind of table designated for, hey, do I send traffic or do I not send traffic? And how do I check to see if it's authorized, essentially? And then source route bridging, right? Used on a token ring network. We'll talk about token ring and topology, I think, later on in this lecture. So we have switches, right? Switches are a big upgrade, huge capability upgrade over a hub, right? Each individual port is its own lane or highway to be able to send traffic down. So this scales super well, right? Like you can have 100 computers plugged in there, and nobody's fighting for time to be able to send messages out onto the network. Okay, everybody has their own lane, and they can send as much or as little traffic as they want, right? And so this operates at layer 2 of the OSI model, or data link layer. Okay, and there's 3 different types of switches. Okay, there's unmanaged switches, which is what you're probably going to buy from Best Buy. Okay, as little configuration as possible, or the configuration's done via a graphic user interface that's super user friendly, easy to use. A managed switch is what you're going to use it at an organization. Okay, Cisco is probably the absolute master here of producing managed switches and having adoption in the market. Okay, this is where you have to go in with like a command line, and you have to know the commands that you need to program into there to be able to get the switch to do what you want it to do. And then layer 3 switches, they don't route across the internet, but they can route across an inter-network. Okay, and so that has hybrid switch and routing functions. Next, we have routers. So routers are the king. Now, one thing I should have mentioned before is there's a price difference between all these technologies, right? Implementing hubs organization will be super cheap, but you're going to have a lot of problems, right? Shy away from hubs. But you can upgrade from hubs to switches for a little bit more money, and have all that capability. And then the upgrade from a switch to a router is pretty significant. Okay, but you only want routers in specific areas, right? It wouldn't make sense to rip out all the switches in your organization or replace them with routers. These kind of just need to be edge devices to be able to route across the internet. Okay, these work at layer 3 of the OSI model, and another huge aspect of this that I didn't mention because we haven't gotten into the OSI model yet, but routers use something called logical addressing. Logical addressing is just a really fancy way to say that they have IP addresses, okay, internet protocol addresses. Switches operate off of physical addresses. Physical addresses are MAC or media access control addresses. You may also hear them referred to as burned-in addresses, BIA, but that's basically a MAC address. And real quick, just to show you the difference, in case there's anybody out there that has not seen this before, I'm going to pull up mine and just show you what the difference is, right? So here's a physical address, meaning MAC address, and we're going to go into this more, but just so you can put visuals to this. And then this is an IPv4 dotted decimal notation address. Okay, and then we have IPv6 up here, but we're not really going to get into IPv6 a whole. Routers use something called a route table. And then depending on the type of router you're using, usually Cisco routers have this proprietary protocol that they use when you plug them into another router called Cisco Discovery Protocol, or CDP. And CDP basically says, hey, I'm a new router, I got plugged into you. Let me learn about the routes that you know about. That way, if I need to route something, I know, what routes you have or what routes this other switch has and who I need to send it to. Okay. This statement right here, dynamic, constantly being updated. And that's really true. So these route tables, I forget the specific times that route tables are updated. I want to say it's like maybe every 90 seconds, but basically it sends out a little message to that other edge device that says, hey, 1, are you still there? And 2, the routes that you know about, are they still active? And if they're not active, they get removed out of the route table. Next, we have modems, and modem is a word that combines modulator and demodulator together. And so, for what this looks like in your home, and your internet service provider has provided you like an all-in-one device that can do routing, switching, modulation, demodulation, but this turns analog signals to digital signals and digital signals to analog signals. Okay, there's a lot of different types of modems out there: direct subscriber line, cable. There's some wireless modems out there. There's even some modems that you can find on a power line. Okay, this also operates at layer 1 of the OSI model, which will again make more sense when we talk about it next week. Here we have a wireless access point. Okay, a WAP. And so this is a picture of maybe something that could be sitting in your house to be able to provide you Wi-Fi access. But just know that the wireless access point, Wi-Fi hotspot, kind of like synonymous in naming. Okay, but there's special considerations there. So ease of use versus security, you're going to hear us talk about that a lot throughout your time here in the program. You want to be able to freely do your job, right, in an enterprise setting, or freely use the internet in a personal setting, instead of being able to be so locked down that everything is too hard to use. Okay, so that's ease of use versus security. Borderless extension to wired networks, right? So we call this bleeding whenever you can see your Wi-Fi network outside the walls of the building that it's destined for. Okay, and that's a security vulnerability if someone can see that. There is a way to turn down the power on your transmitter, on your router, to try and keep it within the boundary, but again, it's imperfect, right? Because you're talking about radio frequency. Open versus closed. So open means that you can just log in. There's no, password, no captive portal or anything like that to block you. You can just get onto the network and use the internet. A closed wireless access point means that some sort of mechanism has been put in place. You need to log in with a password. You have a captive portal you need to enter information into. They have their own encryption protocols, authentication methods, a wide variance in managed and unmanaged types of devices. All right, let's talk about firewalls real quick. So this is not an all-encompassing list of firewalls. In fact, where it says like next generation, multi-level factor inspection, the more industry-aligned term here is UTM, or Unified Threat Management. So I would definitely take a note of that. And depending on who you study for too, like CISSP, CompTIA, they have different naming for firewalls, and sometimes they add their own types of firewalls. So just know, like, this is the set that we want you to know about. Okay, and these are pretty ubiquitous, but I'm just saying, depending on who you study for, they might have other ones as well. So the first one, the most basic and the fastest at being able to filter the traffic, is a packet filtering firewall. Okay, there's only three things that this packet filtering firewall will take a look at, and that's source, destination IP address, transport protocols, and ports. And it's going to check all that against the database that it has to say, hey, what's configured, what's allowed, and what's not allowed. Hopefully it's default deny, but and we'll talk about what that means too here in a little bit. But essentially, it checks this database, says, hey, I know where this is coming from. I know where it's going to. It's via an authorized port and protocol, so I'm going to send this through. Now, if it does not meet that criteria, then it drops the packet and it doesn't go anywhere further than the firewall. None of these solutions are perfect, just so you know, though. So the next kind of upgrade from a packet filtering firewall is a stateful inspection firewall. Okay, that's going to maintain state information from one packet to another, ensuring that information stays consistent, right? It also is going to use that state table and rule set. It's on monitoring open connections. Okay, and so if let's say, for example, if a connection closes down and then an outside entity tries to reinitiate that, the firewall will say, hey, nope, this connection was shut down. This conversation's not happening anymore. You need to go through the channels of reopening a new connection, right? Because what we just described was called a replay attack. And so it's decently good at thwarting the, what was it you saying? The replay attack, sorry. All right. Again, still using rule sets though, so it's got to meet the rules that are configured for it, and you as the operator have to configure that. Next, we have circuit level gateway. This is going to work at layer 5 of the OSI model, and it's going to monitor TCP handshakes, which we're going to talk about here in just a little bit. There's a 3-way handshake that occurs in order to basically say, hey, I need to ensure that you're going to get my information. Okay, this is kind of like an enhancement to packet filtering firewall. It's also an upgrade over stateful inspection. It's going to be utilizing, you'll get really into the weeds in 326 on the send and ACK flags and sequence numbers, but basically every packet that comes across the network has its own unique serial number, right? And so the circuit level gateway firewall is going to be tracking all of that to ensure that there's no foul play occurring. And then we have application proxy firewall, also known as a bastion host, right? So bastion host is a fancy term to say that that device has been locked down to only do whatever job it's destined to do, right? All other services and protocols and everything else has been turned off except for what is actually needed. So this operates at layer 7, or application layer of the OSI model, and it basically acts as a main in the middle. Okay, so you as the client, let's say you want to go to example.com, the client system doesn't particularly see this, okay, but the request is going to go straight to the firewall, and the firewall, depending on what's configured, will either allow or deny that request to go on. Because example.com is benign, it will forward that traffic on to the server that it needs to connect to. The server will respond and say, okay, you want to access this website, here it is. It'll send it straight back to the firewall. The firewall screens it again to say, does this look malicious, essentially? Is it coming from a known IP address, whatever it's configured for? And then if it all checks out, it sends it back to the client, but the client thinks it's talking to the server thinks it's talking to the client. Next, we have next-gen firewall, also known as unified threat management. But essentially, the issue here was that organizations were having to subscribe to a lot of different vendors, which introduces a whole different level of attack surface when we talk about vendor risk. And so, you might have a firewall from, I don't know, Bitdefender, you might have spam filtering from Yahoo, you might have antivirus from McAfee, right? That got really difficult to manage. And so now what occurs is that you buy an all-in-one solution from a specific vendor, okay? The vendor may provide you antivirus, VPN, spam filtering, quality of service management, which quality of service really important to take away from this 301 class because it's going to come up, I think, for the next couple of weeks, basically, is you can basically prioritize the type of traffic on your network. Okay. So let's say at work, you guys have VoIP phones or voice over internet protocol phones, and you want to make sure that all phone calls have enough bandwidth to be able to go out and make the phone call, right? You could do that. You could set aside quality of service management for, your VoIP traffic. So again, the purpose behind this was to consolidate. Next, we have intrusion detection systems. This is actually a passive type of protection mechanism for networks. It has pros and cons, right? It can be hardware, software. The pros and cons, the pros are that it doesn't take any action on your network whenever it thinks something is occurring, right? Like an attack. And why is that a pro? Well, sometimes you have sensitive business stuff that if this thing just shuts the network down, that can be a problem too, right? Better to deal with the compromise in real time than having the network shut down. But again, it depends on where you work and what you're doing, okay? The industry terminology for this, and this is really important, so if you fall asleep, I need you to take this down. You might have a quiz question on it, is that when you configure these intrusion detection systems or intrusion prevention systems, it's called tuning. Okay, we tune these devices to the best of our ability. We want to reduce what's called false positives. So that's getting notifications, hey, an attack is occurring, but when there's not actually an attack occurring. And then false negatives, which is the worst, meaning that it did not detect that an attack just occurred. So at the heart of this IDS solution, it is designed to either send emails or text messages or just contact the network admins or whoever is designated, really, to say, hey, there's something going on the network. It meets our predefined criteria for a potential attack. It needs investigated, right? That's all that it requires, all that it does. The intrusion prevention system, on the other hand, which can be hardware or software, takes action, right? This is an active defense where, again, if tuned perfectly, but nobody's perfect, this will block IPs, shut down ports, whatever it needs to do to block the attack from, going any further. Okay. And a lot of times these devices have become merged. Okay. So when you go out there in industry, you might buy a device that you configure to act as an IPS or an IDS, depending on what you need it to do. And then next we have data loss prevention or DLP solutions. So data loss prevention is pretty straightforward, honestly. I mean, it wants to screen the data that's trying to leave the network for sensitive stuff. And so it doesn't let things like social security numbers or credit card numbers or, I don't know, blood type, like whatever you configure it for, really, to be able to leave the network. That email will never get sent. That document that you attach with a bunch of socials will never get sent. And so it can also apply to instant messaging, web traffic. So DLP solutions are very important for sensitive environments. All right, so let's talk about the different types of networks. So here we're going to be starting from a top-down approach, right? We talked about how the WAN is global. We're going to be moving into the MAN, so intracity kind of area, and then your office in the LAN. So physical versus logical topologies. Okay, so a physical topology are going to be how the actual physical cabling and network connections work, right? So it is like a one-for-one documentation of, or I should say, representation of what you have going on. A logical or signal topology could very well be different. Okay, that's how these devices communicate with each other. Okay, how the signals act on the network. And so it is important to lay that foundation before we discuss any further. So next we have the wide area network. Again, this is the global communication network. Okay, this is the internet, right? And it consists of really, I like this picture a lot down here because it kind of puts it all together, right? There's coax cable going on from building to building. There's telephone wire that has to be able to transmit some of the information as well. There's satellites up there. There's microwave communication. There's ground base stations for satellite communications, where the satellite and the ground base station have to be able to communicate to each other and have somewhat line of sight within the footprint of the satellite. Fiber optic cable connecting certain buildings, right? All of these technologies and these transatlantic cables have to be able to work together in order for us to be globally connected, okay? Now, a wide area network can be private or public. Public is going to be that in the internet, okay? But you can have a private WAN, right? If you had a, let's say you worked for a company that was global, that had their own intranet, right? That could be a private wide area network because only employees of that company can have access to that. This is definitely a combination of wired, wireless types of networks and technologies as well. And the people who are going to be setting all that up, it's going to be global international providers as well as your internet service providers. Next, we have the metropolitan area network, MAN. Okay, we talked about how this is certainly a much smaller footprint than the WAN. This could be still as big as several miles apart, right? This could also be public or private. Think like if a organization owns multiple buildings within, let's say, the city of Houston, city of Austin, doesn't matter, and they have their own intranet that they allow their employees to work on, right? That would be an example of a private MAN. Public MAN is the other example that I gave, where whatever one of those Texas cities that allows or has put in infrastructure to support Wi-Fi for their downtown area. I mean, that's a public metropolitan area network. Next, we have our local area network. Again, small office, home office is kind of the thing that should be ringing, in your head here, where you have a combination of devices, but the geographic footprint is very small. Okay, some of the devices you might have: laptops, desktops, mobile phones, Xboxes, PlayStations, whatever it is, right? Printers, they're all part of the local area network. Some topologies that we'll talk about. This is a bus topology, okay? This is where there's like a central line running through. All information gets transmitted on that bus line, okay? There's a star topology where there's a central hub where everybody kind of communicates through that central hub. A ring topology where devices are connected to each other and able to transmit basically by sending through each other. Now, there was it's kind of deprecated at this point, but it's called a token ring network, where if you will, let's say you have like the talking stick, right? So whoever has the stick can put messages out onto the network, and then once they're done, they take the stick and they, metaphorically, pass it to the next computer and say, okay, now it's your turn to talk, and then it's your turn to talk, right? That was the token ring network. Let me go back here. So next we have a mesh network. This would be considered like a full mesh, right? And there's a lot of redundant links there. And that's the whole purpose of running a mesh network, is that you have redundancy built into your network. If something fails, there's a lot of other ways that the information can be passed around the network, okay? But it's wildly expensive to do a full mesh network, whether you're doing it personally or at an organizational level. Generally, most people opt for a partial mesh, right? Which could be considered this tree or hybrid approach, where either you have this top-down approach to be able to, in a hierarchical manner, lay out your network. But this hybrid approach is probably more so representative of a partial mesh, where not everything is fully redundant, but you do have some redundant links in there in case something fails. There are other options out there. Next, you have your personal area network. Okay, so this is going to be things that are basically just around your body. Okay, your individual personal compute devices, your phone. Okay, you may have which is a small computer essentially, and you may have like an iPad or a tablet, PDA, gaming devices, like a Nintendo Switch or something. Like those are all examples of personal area network, and they utilize wireless technologies like cellular, Wi-Fi, Bluetooth, near field communication. NFC is going to be that technology where if you're using Apple Pay, Samsung Pay, Google Pay, whatever Pay, right? Like you have to put your phone almost on the pad. That is near field communication. Okay. Some other types of networks, there's campus area network, which most people kind of genuinely kind of gravitate to, like college campus area network, but that's not necessarily true. A campus area network is just a multiple local area networks connected together. Military base could be considered a campus area network. There's also the body area network. This is a wearable computing devices. Your Apple Watch is considered part of the band. The near me area network, right? Wireless network of devices in close proximity. So if you have a printer that you can connect to wirelessly, that could be a near me area network device. Near field communication, I just talked about that. Internet area network, it's the internet. Right. And so this slide's really kind of dedicated to that. It's the internet, it's growing exponentially every single year. I'm not a big fan of this Internet Live Stats website. But you can go out there and take a look, and it's supposed to keep track of like how many like Google Hangout accounts have been made, and basically track how big the internet has gotten. That was just one metric. All right, shifting gears, let's talk about network attacks and get back to the security portion of this. Okay, so there's four main threats to network communications. There's interception, modification, fabrication, interruption, and each one of these are attempting to degrade one aspect of the CIA triad, one or more, I should say, actually. And these can be human or non-human, malicious or non-malicious, just like we talked about in week one. Interception is going to be a confidentiality failure. Modifications and integrity failure. Fabrication is kind of a confidentiality integrity. It floats between, I say. Interruption, availability, 100%. Okay. So again, interception, eavesdropping, utilizing tools like Wireshark. I mean, there's a ton of tools out there. ZenMap. And basically, you have unauthorized access to information that you shouldn't have. Okay, definitely a confidentiality failure. You can do this via packet sniffing, where what packet sniffing, Wireshark. Cable splicing, right? So you can cut someone's cable, resplice it to be able to, let's say, connect it into a hub so that you can connect into the hub and see all the traffic. Inductance tapping, that's where you basically, there's a little bit of energy that comes off of, let's say, unshielded twisted pair. And theoretically, you could be able to capture some of that energy coming off and be able to read what's going on in the network. And there's RF interception, right? So wireless networks, the RF radiation is being blasted everywhere. And so there's tons of tools that you can use to be able to latch onto the wireless network and then try and break into it. Next, we have modification. So that is an unauthorized change to data, right? That is directly an integrity failure. That's where you can modify data en route. So the example being like if I sent a email to a class saying, hey, welcome to CYBV 301. But by the time that message got to you, it said, hey, everybody gets a 100. That would be a huge integrity failure. Okay. And that can happen. Modification doesn't have to be human and malicious, right? This thing can occur like sometimes if you've ever had your computer shut down, let's say the power goes out and your computer just shuts down while you're in the middle of a Word document or something like that, that can corrupt the file to the point that you can't reopen. Okay. And so, or maybe it saved like half of it, right? Next, we have fabrication. Okay, so with fabrication, you have unauthorized creation of network data being put out onto the network. And this can occur via sequencing, substitutions, insertion, or replay. So with sequencing, right, you're taking data fragments and arranging them in an order that it wasn't supposed to be in. With substitutions, right, you're splicing or replacing data with different data, right? Insertion, we have data values inserted into a stream to change transactions, right? So there's types of attacks that you can do where you change the price in your cart for a specific item and try and pay nothing for it. And then there's replay. We kind of talked about replay earlier, but the captured data is transmitted back onto a network to try and make a previous conversation open back up. Definitely an integrity failure, but potentially leads to the confidentiality part as well. And then interruption. So when we talk about interruption and attacks on availability, a lot of people think that this is something that has to be like, a complete halt, a huge detriment. But that's not necessarily true. You can achieve denial of service or even distributed denial of service an attack on availability, if you just degrade the network even just a little bit, right? So if it takes you normally 30 seconds to power on your computer and then get to your work files, but now it takes you 5 minutes, right? Like you're causing some serious damage to the organization in terms of productivity. So next we have network security considerations. Okay, so here we security versus usability conversation again. There absolutely can be too much of a good thing. There can absolutely be too much security. You got to think whenever we go into these organizations and we're trying to help them with their cybersecurity hygiene, the company's whole premise is not cybersecurity. Okay, so let's take Ford, for example, the automobile maker. They're what makes them money is selling cars, not cybersecurity, right? So cybersecurity is one supporting pillar to the overall business framework, right? So you're going to be fighting for budget, you're going to be fighting for capability and all these things, right? Because you're just one sliver, right? Like you can't have too much security because then you start eating away at the funds that from selling cars and the bottom line of the business. So you just need to take that understanding with you. So again, but kind of deviated away here. Security versus usability. You should be able to do your job with little to no interruptions, right? If you lock things down too much, you're going to have your users circumventing your security solutions at every single turn. Security by design. So this one basically states that with the first time that you do something, let's say we're opening a new office in Chicago, let's plan this out. Let's put the security devices in first that should be there from the start, right? Instead of saying, hey, let's just get the network up and then we'll worry about security later, right? Like you need to bake it in. Okay, you need to do it the first time, you need to do it right. When you start doing bolt-on solutions and talking about retroactively fitting things and adding in different solutions at later times, then you have to do risk assessments, and it gets really costly. And it has to be like a business justification for it. Okay, so it's just better if you can just build it in by design. Attacks and command and control. That's what C2 stands for. We have network-based attacks and client-side attacks, okay? So network-based attacks are going to be a lot more difficult, right? Easier to mitigate, less fruitful for attackers. They're essentially looking at, like, this is akin to the castle and moat design, right? Where the individuals are attempting to go through the moat and break down the wall and get it to the middle of the cities, right? Or whatever you want to call it. A client-side attack is like the helicopter comes in and you rope line straight down into where you need to go. Okay. And the way this actually looks is that, for example, HR, right? HR is a great example for client-side attacks. Their job every day is to basically take in resumes from random people across the internet. And so if someone puts a malware-laden document and labels it their resume, sends it to HR opens it up, boom, they're infected, right? Way easier than trying to scan ports and IP addresses and trying to figure out if there's a misconfiguration on an edge device. Like that gets really hard. Not that it doesn't happen. It certainly does happen. In fact, some of the biggest breaches that have occurred, like the SolarWinds breach, absolutely occurred by a network-based attack. But when you're talking about path of least resistance, higher chance of success, client-side attacks, absolutely. Inbound and reverse C2 connections. Again, C2 stands for command and control. Inbound means that the server is talking to the infected computer. Okay. A reverse C2 connection means that the computer is reaching out to that malicious server for instructions. All right, let's talk design requirements. Okay. And so whenever you're designing your network for your organization, you got to start with like, what does the organization do? Okay, what type of demands do we have on our network? How much bandwidth do we need to pay for? How much availability do we need to pay for? Right? There's this principle, or not principle, but concept that we call it the rule of nines, right? For availability. And so if you pay for 5 nines, which is 99.999% of availability, that means you're only down for just a couple minutes out of an entire year. Okay, so very small amount of downtime. And every 9 that you take off, there's more and more time that you're down every year. But when you're paying for 5 nines, it's an astronomical price that you have to pay. Amazon absolutely pays for 5 nines. Facebook, like all these big, huge organizations pay for 5 nines because they kind of have to, right? If they're just think if Amazon was down for 5 minutes, how much money they would lose. It would be staggering. You also need to flood network security devices to areas that house sensitive information. It doesn't make sense to do this not ubiquitous, but a like level approach to your entire network. We're going to talk about different defense postures and stances you can take, but a everything is sensitive kind of approach doesn't work very well. Okay. And so you should figure out where your sensitive information is located and lock down those pathways. Okay. Are there, so this says, how is the organization structured? You might have to have special considerations for different parts of the organization. But you also might have regulatory requirements, which is what I wanted to say. I think there's a catalyst here. But either way, so yeah, it's 2 slides from now, sorry. But so your regulations will also dictate things like so the New York Department of Financial Services cybersecurity regulation states that you have to have things like a chief information security officer. You have to have system and application logging. You have to have penetration tests done every 6 months, right? Those would also be considerations for you going into your design requirements. Okay? We talked about data sensitivity and where that's really kind of the forefront, right? You need to understand those pathways, being able to understand your requirement for integrity, data integrity. Do you have anything that's critical or critical infrastructure? I mean, critical infrastructure is like the power grid, right? How important is it that the devices that are monitoring that are accurate? That's pretty significant. And then we talked about data availability. Definitely going to be different by the sector that you're in. Information potentially being segregated logically or physically. Okay, we talked about by regulation, but you may also need to separate data by function or security policy, depending on how your organization is set up. And there might even be different access controls on those different silos of information. What needs to be protected? At a minimum, things like personally identifiable information, social security number, okay, protected health information, payment PCI or payment card industry data, so your credit card number, okay, sensitive data like intellectual property, competitive data that makes your company competitive in the market, classified data that really ends up costing lives when classified data becomes compromised. So these are network security zones. If you fell asleep at any point during this lecture, I need you to wake up because you're definitely going to need this for your quiz. This specific slides and some of the next slides are going to be really critical. Okay. So there's these lines here, right? We have the public and untrusted open internet behind a firewall here. Okay. The DMZ or demilitarized zone is somewhat trusted. Okay. So people from the internet can come in, access your web page, right? They can use the email server if they have an account. They may be able even to use the internet on campus, right? Like a guest internet, okay? Maybe there's a file transfer server that they have that you can access. So that's, again, this firewall is super loose. It's looking for major level attacks, but allows people from the internet to come in. Now, nobody should be able to go from the internet to the trusted and restricted zone. This firewall should be on lockdown, okay? So nobody from the internet goes all the way down. This should be able to block, anybody that is not authorized. Okay, business purposes only behind the trusted and restricted zone. So next we have access control principles and fundamentals, right? So the principle of least privilege means that you should have the permissions assigned to you that for you to only be able to conduct your job and nothing more. Okay. The principle of need to know, the example that I give here is like in the military, right? If you have a secret clearance, that doesn't mean that you have access to all the secret data, okay? You have your little slice of the pie that you work on, and that's it. Separation of duties, the example that I give here is the person who writes the check shouldn't cash the check. which makes pretty basic sense, I think. Right? In that situation, ideally, there should be a person who writes the check, person who cashes the check, and then a person who audits the entire transaction to make sure that person 1 and 2 did not collude. And then rotation of duties. This principle I've literally never seen implemented, but it is something that you will learn in your academic studies. But this principle states that every 6 months, your team should rotate positions. And the thought is that as the oncoming team member is learning how to do that specific job, learning what the previous person did, they can uncover fraud. Okay. And then with a secondary benefit of people enjoy learning new positions all the time. Next, we have access control fundamentals. Okay, so there's discretionary access control, which is going to be managed by the user. So when I go to my desktop here, and I go to this picture, and I right click it, and I go to properties, I go to security, I can set here who I want to have access to this. If there were multiple users on this computer, you would see them here, and I could define whatever I wanted to for them. That's discretionary access control. Mandatory would say that I have to have a specific clearance, right? Like a secret clearance, top secret clearance, whatever it is. And then I have to be matching my request for data with my clearance, right? So if I have a secret clearance, I'm accessing secret data, TS. Role-based access control is going to be the most common implementation that you're going to see in industry, right? It's super easy to manage. So basically what happens is that they create these buckets of individuals, right? So let's say executives, IT, sales, right? We have those 3 groups. And as people join the organization, you create their account in Active Directory or the role-based or the LDAP solution, and then throw them in. Hey, this person is a newly hired executive. Throw them into the executive bin, and then they get assigned all the permissions they need by being in that bin. Okay. Rule set based access control. This specifies rules for individual objects. Okay, so if I wanted to say that I only want my employees to access the internal network from 8 a.m. to 5 p.m. and after 5 p.m. Their access is shut off from the network, I could do that. Or I could say something called geofencing, where they're not allowed to access the network unless they're within 50 miles of the office. Okay. List-based access control puts a list of permitted users or subjects for each object, which is a resource on the network. The token-based access control is a list of permitted resources for each subject or person. When defining your access control policy, you have to think about the 5 W's, right? The who, what, when, where, why, and how. What needs to be controlled? How are they accessing it? What's the business justification? What are the technologies we're using in place to make this happen? And how long does it need to be going on for? Next, we have basics of traffic filtering. Okay, so default deny is what all of your devices should be doing, right? And kind of we're really kind of talking about like router switches and firewalls here. So basically, what default deny means is that whatever predefined rules you have configured in there, it's going to check that traffic to say, hey, does this traffic meet those predefined rules? If not, I'm throwing it away. I'm not forwarding it. It could be bad. Whereas default allow says, you know what, it doesn't meet any of my rules, but I'm just going to send it out a chute and hope for the best. Okay. That's not good. You want to make sure and verify any solution that you apply to your network that you have it configured for default deny. You can filter traffic in a lot of different ways. Okay. You can do it directionally. Is it inbound, outbound? Is it taking a proxy to do that? IP address, MAC address, ports, protocols, specific applications, right? How big the traffic is. These are all things that you can configure your solutions to be able to filter on. So let's talk network design considerations. Perimeter-based flat networks versus segmented networks. Okay, so again, if you fell asleep, you're going to have a lot of questions on the quiz, so I need you to wake up on these next diagram slides. Okay, so this perimeter-based flat network that we have here, this is very simple. This is also a single point of failure right here, right? If this firewall goes down, potentially your the internet has access to the internal network, and that would be really bad. And so free flow of traffic behind that boundary. Sorry, my son was behind me. Super cheap to implement, right? And so this is probably what you're seeing at your home right now, right? Like you have your internet service provider solution that they've given you. It may provide basic firewall, but you just have the one firewall essentially separating you from the internet. Okay. Now at an organization, if you have this, you can start adding in remote users, and then that really increases complexity. Okay, again, this is a flat network. We have a single point of failure here. A lot of questions on like how are we implementing the remote users and securing that down. Okay, is there a required business justification for being able to do that? The infrastructure to support is going to be a lot more when you start adding remote access. And then now you start partnering with another company. What happens if they have a data breach, right? How do you protect against that data breach spilling over to your network, right? It could be a pivot point. In fact, I don't think I showed you Darknet Diaries, but Darknet Diaries is a really interesting podcast to listen to. And they have Xbox Underground is one of their episodes, and they talk about how they use that Xbox. They got into like Microsoft's internal network, and they use that to pivot to a bunch of different game developers and get into their networks because they had partner access to those companies. Next, we have virtualized segments. Okay, and so this is where we're turning from a flat network design to a segmented design, and you can do this logically or physically. We'll talk about that in a second. But you can see like this box over here is almost like having a completely different network. Okay, so if an attacker gets in and he's free roaming back here, he has to essentially re-break into a whole nother network to get into this box, right? And that can be as complex or as involved as you configure it. Next, we have bring your own device solutions. This is a terrible idea in every capacity. The reason people do this is like the organization doesn't have to buy computers for anybody anymore. Users like to have their home device that they use every day to bring into the office, but this should be avoided at literally all costs. Okay. This whole conversation gets really complex when you start talking about like, everybody has different applications, different operating systems that they have loaded on their stuff. And when they bring it into like the office environment for a BYOD environment, let's say, they have something called NAC or network access control. And so that when you go to connect to the company intranet, the network access controller will say, hey, are you up to date on your antivirus? Are you up to date for your operating system patching and all of this stuff, right? It'll give you just enough bandwidth to be able to update all of that before allowing you onto the network. So essentially, there's also a minimum threshold for you to be able to access that internal network as well. And then we have segmented networks. So this network that you have here is a lot more secure than what you saw in that flat design. Okay, so the internet here, we have our DMZ hanging off over here, where internet people can access, our email servers if you have an account, or web page, whatever you have hanging off in your DMZ, essentially. However, behind here, let's say we have IT, sales, and executives again, right? Each one of these firewalls can be configured to have as strict of rules as you want, right? So, but ideally, nobody from the internet should be getting past this one router. But if they do, then they're going to hit this other router, which should be even tighter. So breaking into sales is going to be difficult. You can also configure these routers to say, hey, I want sales and IT to talk to each other, but I don't want executives to be able to talk to IT, right? You can configure that. However you want to do it, you can do that. It has a very high level of granularity that you can do. Some segmentation techniques, right? We can literally buy different switches, right? You can stack switches in every office building that you want. That would be a physical segmentation technique. We're buying physical switches and putting them wherever you need them. However, switches have this capability of doing virtual segmentation, right? A virtual local area network. And so you can buy one switch and hang everybody off of a VLAN where you can do the exact same thing if you bought physical switches, right? So I'll put finance in VLAN 10, sales in VLAN 20, management in VLAN 30. I'll configure that management can talk to finance, but management can't talk to sales. However you want to do it, right? Is the point. But you can do this logically instead of physically. There's also cloud-based schemas for being able to do that. There's things like public cloud, hybrid cloud, community cloud. Public cloud, everybody's data is basically just logically separated on the same server. And that can be good and bad, right? Low cost, high security concerns, I would say. Private cloud, high dollar. You're paying super high dollar to have your own space. But you know that nobody else's data is walled up against yours. All right, here's this castle and moat design that we talked about before, right? We have some defense in depth methodologies that we're going to talk about. When we talk about network defensing, again, you're trying to get past this border, this moat, trying to break down the wall just to get all the way up here, right? Whereas a client-side attack, you're flying with the helicopter, or maybe you have an F-35 that you can drop some 500-pound bombs on and just take it all out. That's what a client-side attack is like. So next we have uniform protection, defense in depth. This is where I was talking about where you're applying like the same level of protection to all of your devices. That is not, it's not feasible, it's not responsible, but it is a way that you can potentially deploy, right? But basically this says, agnostic of sensitive data, we're just applying the same security on all of our devices, okay? Protected enclave steps it up. Okay, now this comes with the first recognition of, hey, we might have sensitive data. We might want to wall that sensitive data off. We might want to flood specific resources to where our sensitive data is. We might want to have additional things like firewalls, VPNs, and segmentation into here. But then we have information-centric defense in depth, and this is the best because this identifies critical assets, where sensitive information is, does risk analysis, why is the data important, how are we protecting the data, who has permissions, what level of permissions, okay? We're doing things like whitelisting. Whitelisting is very difficult. There's a concept of whitelisting and blacklisting, where whitelisting is where you say, hey, these are the only applications that can be used at the organization, whereas blacklisting takes the other approach and says, hey, these are known bad solutions that you can't download, everything else you can. A lot of administrative overhead in doing whitelisting. And then next we have threat vector based defense in depth. And so this recognizes that certain outlets cause mayhem essentially. So I'm sure most of us have worked in an organization where the USB ports were disabled, or the CD-ROM or floppy disk drive was disabled. And that was because they were employing a threat vector-based defense in depth, where they said, hey, you need to get special approval in order to do these specific things, because there's things like media drops, where people take these USB sticks loaded with malware, throw them out in a public area, and then people love to just stick them in their computer like they don't have malware on them, but they do. All right, that was a lot, I know. And so I'll stop here. What questions do you guys have? Jaquan, I think you had something for me, right?
Yep.
What you got for me?
So for final exam, you said we have to do all 8 weeks.
I'm sorry, say that one more time.
I said for final exam, we have to cover all 8 weeks.
Yes.
Okay.
But I would say, so week 7 is more so a review of everything that we learned in the course. There's a little bit of new material sprinkled in there, but I would say after our week 6 lecture, you're pretty much ready to take the exam. The other thing to take note of too is that this class is an open note, opening internet, like you just can't collaborate with other people. So what I would do when I go to take my final exam is pull up all the PowerPoints, have the book ready, and then go take it.
Okay.
Does that make sense?
Is there any way we can have access to the quizzes we did?
You
where
should
we can
have
see
access.
which questions were wrong?
You should be able to see. Let me double check here.
It gives you the answers when you submit it. It lets you know to which one you did wrong.
Yeah, it looks like it says. So just so you know, though, the final exam is not going to be a regurgitation of any of the quiz questions that you've already gotten. It's completely different.
Oh, okay.
But I will go in and enable so that you can see the questions on the quiz in case you
I
want
was
to use
just
it
thinking
to
to
help study.
practice week 2 for CyberOpus.
Okay.
So
Yeah,
that's what
yeah. So you'll definitely need the command line interface for
Yep,
the
got
final
it.
exam.
Yep. So that's what I was looking for. Okay, if we get some practice from the questions.
Yeah, yeah, absolutely. Okay. So I just went in and enabled that for week 2 and week 1. I'll get all the rest of the weeks done too, though.
Okay.
Cool. What else do you guys have for me?
That's all. There's something in the chat. I think so. He posted.
Okay.
Unknown caller.
So the insertion fabrication. Can you explain that one to me, Kieran? Do you have a mic, Kieran? Okay, no worries. So I'm trying to interpret your question there. It says, does the insertion fabrication equal the modified program involving virus code? So I think when we talked about fabrication earlier, that's talking about putting unauthorized messages or data onto a network, which is different than the insertion method of how malware can be inserted into a legitimate program. Does that make sense? Yeah, yeah. All right, cool. Any other questions for me then? If not, then I hope you guys have a great week. I wish you the best of luck on the quiz, and don't hesitate to reach out if you need anything at all. Okay.
All
Have a
right.
good one,
Thank you.
guys.